Your tuition money goes a long way. Good morning, everybody. So we're going to continue our discussion on linear equations and Gaussian elimination. Let's look at the 2x2 substrate that we had last time, where we talked about making various measurements. So we discussed how we can shine a beam through the first row, make a measurement. These are all unit dimensions. So you'd get x1 plus x2 equals some measurement. That would be your first measurement. So this would lead to B1. This would lead to B2. So this one involved x3 plus x4. Actually, let me space it out. So B1. Then we had x3 plus x4 was B2. And we made a third measurement through the first column, and that was x1 plus x3, which was B3. And we ran into a problem when we said, well, let's make the last measurement, this one, B4. I'm going to call it B4 prime. So that one was what? X2 plus x4 was B4 prime. And we discussed that by combining the equations in particular ways, we realized that the last measurement is actually not giving us any new information. And one of the diagrams I put up on the board was, suppose your x1, x2, x3, x4 are of this form, 1, 0, 0, 1, and compare that with this configuration. If you actually plug these values into the equations, you should be able to easily verify that this system of equations or this set of measurements is incapable of distinguishing these two. And I use the cartoon example of a tumor in the left lung and the right kidney versus the tumor in the right lung and the left kidney, leading to a problematic surgery. So these two are indistinguishable. In fact, you can have other configurations that are indistinguishable. For example, 0.3, 0.7, 0.2, 0.3, and let's see, 0.4, 0.6, 0.1, 0.4. And you can cook up all kinds of, and in fact, an infinity of such configurations that are indistinguishable. So there is something wrong with this system of equations, and Gaussian elimination is a process or a method of figuring out whether a system of equations has a unique solution, an infinity of solutions, or no solution at all. This particular set of equations has an infinity of solutions. And we'll get into the details very soon. There are some systems that have no solution at all. And I'm going to work out this storyline for you in a 2x2 case, not in a 4x4 case. In the 2x2 case, we can draw things easily, and it's much easier to visualize. So if you permit me, I'm going to go into a two-dimensional story. And develop our concepts in there. And instead of using x1, x2, you're probably more comfortable with dealing with xy. So I'm going to use x, y as variables. But when we go to, well, in 3 dimensions, we'll use x, y, z. And in higher dimensions, we'll use x1, x2, and so on. So let's start with an example. And I'm getting this example from one of the editions of Professor Strang's book, which I think should be on your recommended list. I highly recommend that book to you. So I have 2 equations and 2 unknowns. And the second one here is 2y equals 11. So in fact, there is a coefficient of 1 here, just to keep things quasi-symmetric, and quasi-symmetrically labeled at least. So this is my set of 2 equations and 2 unknowns. Okay? I'm going to label this equation 1 and equation 2. Gaussian elimination involves a set of operations that turns this system of equations ultimately into what we call an upper triangular system. So I'm going to give you the final destination of what we're going to do. And that final destination is x minus 2y equals 1 and 8y equals 8. So I'm going to describe the steps going from here to here. In 2D, it's not very complicated. The way we go, so now, suppose we are here. By hook or by crook, somehow I've converted this set of equations into an equivalent set, which is this one. How would you solve for x and y? Talk to your neighbors. So don't worry about the process that took us from here to here yet. Tell me what you would do to solve for x and y. Okay. Do I have a volunteer? You are? Neil. Neil. Oh, you volunteered last time too. Go for it, Neil.
So you can find out what y is by dividing 8 on both sides.
So you solve for y. Y is 1.
And you can plug it in. You can plug in y.
Speak loudly so everybody hopefully can hear you.
You can use back substitution to plug in y in the first equation to solve for x.
So substitute in E1 prime, and so you have x minus 2 times 1, y is 1, equals 1, and that gives x equals 3. Okay? So this is essentially the bulk of the procedure for Gaussian elimination. It involves a step called forward elimination that I haven't described yet. This is step 1. Step 2 is basically isolate. So step 2, isolate the last variable. In this case, the last variable is y, and solve for it. Okay, so that's here. Notice, if you look at the coefficients, they form a triangle. Everything below this main diagonal that I've drawn is 0. So there's a 0 times x here. If we had a larger system, then everything underneath that main diagonal, all the coefficients would be 0. And that's what happens when you go through forward elimination, which I haven't described yet. So at the very end, since we end up with a triangular system, this is an upper triangular system, the last variable is the only variable in the last equation. And so it's isolated. We solve for it. And then we do, this is step 3. That's back substitution. So we start substituting into the next level up equation and work our way backwards. So when we go, if this had been a 3 by 3 system, then the next level up equation would have had 2 variables in it. So we solved for the last variable in the last equation. We plug it into the next equation. We solve for the next variable. So now we have 2 variables solved for, and we work our way backwards. So that's what back substitution is about. Which leads to our solution. So this set of equations happens to have a unique solution. Things don't always go this nice and dandy. If, for example, we had ended up with a 0 coefficient in the last equation, we would have been in trouble. But before we go there, let me just describe this forward elimination step to close the loop on this problem. So how did I'm going to let you play with it for a little bit before I hash it out myself. Because in the 2 by 2 case, it shouldn't be that hard to see how I went from here to here. Why don't you talk to your neighbors and see if you can figure out what that forward elimination step was. What did I do with my 2 equations? In other words, how did I get my equation 2 prime? Equation 1 prime is the same as the first equation. That doesn't change. That always stays. Okay, Neil is going to pick somebody. No, not your own partner. You have to pick somebody else. So, did you get? So, by the way, I forgot to mention this last time. When I ask you to talk to your neighbors, while you're discussing the problem with your neighbors, decide who's going to be the spokesperson for that group, okay? So that we don't have to spend time. So any of you 4 can speak. You are? Avery. Go for it, Avery. How did I get equation E2 prime?
So you multiply the first equation by -3.
Uh-huh.
And then you add it to the second equation.
I add it to the second equation. So equation 2 prime is obtained by taking the second equation and multiplying 3 times the first equation. If I do that, so I take the second equation, subtract 3 times the first equation. So I have 3x minus 3x. X goes away. And I have 2 minus 3 times minus 2. So 2 plus 6y, and that gives me 8y. Okay, so I have 3x minus 3x plus 2y minus 3 times minus 2y. Of course, that gives me 8y. And I have to do the same thing on the right-hand side. So when I take 3 times the first 3 times 1 and subtract it from 11, I get 8. Okay? Now, By doing this, I have eliminated the coefficient of the variable x, of my first variable, right below in the next equation. If I had more equations, I'd do the same thing with the subsequent equations and get rid of everything underneath x. And then I would go after the coefficients of y below the main diagonal. Now, so in this case, what we've ended up having is a set of coefficients along the main diagonal. Let me use a different color. These coefficients that are right on the main diagonal are called pivots. Okay? Now, one distinction I have to make between the notation or the terminology I use and what's in Gil Strang's book is that regardless of the value of what's on the diagonal, I'm going to call them pivots. Gil Strang only considers non-zero values as pivots. Zero pivots cause problems. And the next example I'm going to give you is one where you have a zero pivot. As long as you do forward elimination, get rid of all the coefficients in the bottom left part of the diagram here, and you have non-zero coefficients along the main diagonal, you're good to go. Your system has a unique solution. Things go wrong when one of those pivots turns out to be zero, one or more. Okay, so let's look at a situation like that. And this board has a problem. So, what could go wrong? What could possibly go wrong? What could go wrong? And the answer is zero pivots. So let's look at x minus 2y equals 1, and 3x plus 2y equals 11. Can you do forward elimination on this and see what you get? Oh, wait a minute. X. Yeah. Oh, no. What am I talking about? I got the wrong equation. So, sorry, this one. Minus 6y equals 3. There we go. Talk to each other, people. Talk to each other. Okay, Avery, I'm going to keep you on the hot seat. Is that okay? Is that okay if I keep you on the hot seat? Okay. So talk to me. What do you do? The first equation stays the same. What happens to the second equation? Huh? No. So by hot seat, I mean, can you continue answering?
Okay, yeah.
You had it easy last time.
So you multiply the top by -3 again, and you add to the second equation.
So you, again, subtract the 3 times the first equation from the second equation. If you do that, what do you get? How many times x?
You get 0.
0 times x. So this is E1 prime, and E2 prime is E2, the original second equation, minus 3 times E1. Okay, so what happens when I subtract 3 times this from that?
You get 0 again.
0 times y equals 0. So now look at your pivots. There's a 1 here. It's certainly upper triangular. This is your first pivot. And this is your second pivot. 0 pivot. Anytime you encounter a 0 pivot, the first thing you've got to do is slam the brakes. You have to stop and look at what's happening. Okay, in this case, Avery, what's happening with the second equation? Am I not getting any solutions, or am I getting an infinity of solutions? Those are the two pathological cases. When things go wrong, when a pivot is 0, you either have a no solution case or an infinity of solutions. So, infinity of solutions. No matter what I plug in for x and y, the second equation is going to be satisfied. And if you look at these two equations, the second equation is 3 times the first equation. So if the second equation had come from some kind of a measurement, just like in our tomography example, 2x2 case, if the second equation can be obtained from the first equation by simply a scalar multiplication, or if we had more equations, by some linear combination of the other equations, then it's not giving us any additional information. So in this system of 2 equations and 2 unknowns, the second equation is superfluous. It's not giving us anything new. And that's why we have an infinity of solutions, because now we're effectively looking at a system that is a single equation with 2 unknowns. And anytime you have fewer equations than unknowns, you have an infinity of solutions. So this is an infinity of solutions. Any xy satisfies the second equation. So E2 prime doesn't give, or I should say E2 doesn't give additional information. Is everybody here so far? Okay, cool. So let's go to another case. X minus 2y equals 1. 3x minus 2y equals, what do I have here? Anything other than 3 should work. I'll put 12. Do forward elimination on this one and see what you get.
I think you mean 3x minus 6y.
3x minus 6y, yes. I didn't have breakfast this morning. Thank you. Even if you figured it out, talk to each other, people. Talk about basketball, football. I don't care what you talk about. Give your last 4 digits of your social security number. I don't care. Bond. Okay. Avery will now pick the next person. Over, Avery. Let's spread geographically. So I want geographic diversity and gender diversity, okay? And any other kind of diversity. I'm for diversity. Just pick. Young lady, girl. That's so un-PC, man. My 6-year-old is a girl. My 2-year-old is a girl. Young lady, where? You are? Shoba. Shoba. Are you the spokesperson? Do you want to be the spokesperson for your group?
Yeah.
Okay, go for it, Shoba. What does forward elimination give us? First equation is always the same. So how are you going to get rid of the 3x?
You multiply E1 by 3.
Uh-huh.
That gives you 3x minus 3x, and then it gives you negative 6y minus.
So 3x minus, so you're subtracting E2 from E2 3 times E1. Okay? So you get 0x. Uh-huh.
And then it gives negative 6y minus 6y.
Right?
It's just 0y.
0y equals
Negative 9. No,
12 minus
3.
3. 9. Okay. What can you tell me about the second equation now, Shoba?
There's no solution.
There's no solution. You have, on the left-hand side, something that's identically 0. No matter what you plug in for x and y, you're not going to get a non-zero number, because each of them is being multiplied by 0. Okay? So you have a 0 equals 9 situation. That's not a good situation to be in. So this system of equations has no solution. And of course, we have a 0 pivot. So if I put in the 1 here, look at the upper triangular form, you'll see the 0 pivot right here. Again, anytime you have a 0 pivot, you've got to stop. You can't proceed without doing something or looking at something more carefully. All right, so we've had a case with a 0 pivot where there's an infinity of solutions. And we've looked at a case with a 0 pivot where there's no solution. There are cases where you have a 0 pivot, but the case is salvageable. So one example is 0x plus 2y equals 4. This is practically a trivial case. It becomes more important in higher dimensional problems. Notice, I can't even, so here I have a pivot that's 0, a main diagonal coefficient that's 0. So I certainly can't subtract any multiple of the first equation from the next equation to zero out the x. Right? No matter what I multiply the first equation by and combine it with some multiple of the second equation, I'm not going to get 0x. But this is a salvageable case. We can salvage. And the salvage is usually a very simple operation. And that simple operation is, you have a question or answer? Well, you can't, so the question is it really a pivot if it's not an upper triangular matrix? Let's extricate ourselves from terminology and just see if you can proceed with forward elimination, which is your step 1 in this system. Can you do that? You can? Exactly, so that's my point. So the way you salvage this, and this is, again, I said it's trivial in the 2x2 case. When you're doing a larger set of equations, when you're doing this on a larger set of equations, you might bump into the situation partway through forward elimination. Okay? So the quick solution is, what's your name? Matei. Matei suggested that we flip the equations, which is exactly what the operation is that saves you. It's called row exchange. So row exchange is the only fairly straightforward operation that you can do to resolve a situation where you can't eliminate any of the further coefficients. So in effect, what you're doing is you're relabeling your equations. You're going to keep this as equation 1, and you're going to keep this as equation 2. And this is already now in upper triangular form. So right here, you've got non-zero pivots. It's got a unique solution. I'm not even going to bother talking about the solution. Yeah?
Why not use the usual linear algebra definition of pivot factor in some
The usual linear algebra definition, which is?
which is that after you reach row echelon form, you look at the leftmost non-zero coefficient of each row. So,
OK, I look at the leftmost non-zero coefficient of the first row.
yeah, of each row.
Of each row, OK.
And that's the pivot of the row. In this case, 2 would be the pivot and 3 would be the pivot under that definition.
Yeah, but when you're programming this, you're going to have to do some swapping or relabeling of the equations.
But I'm just thinking that definition is
Because otherwise, you've got to parse through. Whatever works for you, it doesn't matter. But the point is that if you have a situation where you're looking at an equation and you're trying to go through forward elimination, and the leftmost coefficient in that equation that is required to null out all the subsequent ones underneath happens to be 0, then you're going to have to do some kind of row exchange and bring the other one up and then do the forward elimination using that. In this case, after the row exchange, it's already in upper triangular form, so it's a non-issue. But I'm not worried about your understanding of the concept. Whatever you're comfortable with, just do that. The point is, if you bump into a 0 coefficient on the leftmost variable, and you still need to zero out the coefficients underneath that, you're going to have to do some kind of row exchange. OK? All right. Now, so this case I'm going to be done with because row exchange is not a particularly sophisticated operation. I'm going to talk more about the geometric view of what's been happening with the other cases, the unique solution case, the infinity of solutions, and the no solution case. So let's put all of those equations up here again. My unique solution case was what? X minus 2y equals 1. And I have 3x plus 2y equals 11. The next example was x minus 2y equals 1. 3x minus 6y equals 3. And the next example was x minus 2y equals 1. And 3x minus 2y equals, what was it? 12? 12. OK. Now, what do I mean by the geometric view? Well, each of these equations is the equation of a line in two-dimensional space. Could you please plot those lines for me in the xy plane for each of these cases? So plot the equation x minus 2y equals 1 and 3x plus 2y equals 11 on this diagram. And do the same thing for the others. And tell me what you observe. I'm going to give you about 2 minutes, huh? 6y. I keep missing this 6. Thank you. Yeah. OK. Go ahead, talk to each other and see what you come up with. How are we doing? Are we done? Done? No hands? You need more time? Are we all good? Okay. Shobha, you get to pick the next person.
The person with the
Blue
blue hat in the middle.
hat in the middle. Yes, I should point out that historically, if you look more distinctive, you are likelier to be selected. So if you're wearing a shirt that requires a dimmer switch, if you're wearing a hat like that, you're probably likely to be selected. So, and I've had students who deliberately do that, so they're selected more often. You are? David. Do you want to be the spokesperson for your group? Sure. Go for it. So give me the line. What line should I draw here? What's the x-intercept? Okay, give it to me whichever way you're comfortable. I usually zero out one of the variables and see where the intersection is of the other one. So I usually set y equals 0 and x becomes 1, and then I get the other point on the other axis. But whatever you like.
Yeah, so the x-intercept is 1, and
1,
y-intercept is
negative 1/2. Okay? So that's the line. This is the x minus 2y equals 1. This is 1, this is minus 1/2. Okay, and the other one?
second line, the x-intercept is
The x-intercept, 11 over, okay, 11 over 3 is what, 3 1/3? So like that, okay?
and then the y-intercept is
11 over 2, so it's 5 1/2, it's way up there, huh? So it's going to be like that. And the intersection is? Intersection would be your solution, no? What did we say the solution was? 3, 1. So I didn't draw it properly, but this should be 3. And this should be 1. Okay? Now, with this, so the two lines intersect. And in 2D, when they intersect at a unique point. Can you tell me how this relates to the upper triangular form of the equations, which was x minus 2y equals 1? And remember when we did the forward elimination, we had 8y equals 8. Can you tell me what that equation is? Straight horizontal line. That's the 8y equals 8. Y equals 1. Notice, maybe I should use a different color for each of these lines. So let's use green for this one. Okay? So the solution is at the intersection of the white and the green, which is the original set of equations, or the white and the red, which is the upper triangular form equations. Those two solutions should not be different. In other words, solving the set of equations white and green is equivalent to solving the set of equations white and red. The intersection of these two is exactly at the same point as the intersection of these two. So Gaussian elimination does not change the solution. The operations we perform by taking linear combinations of equations does not move the solution. And you can see that graphically in this case. So whether you're looking at the upper triangular form of the equations, the solution is exactly at 3, 1, which is what it was if you were to draw the equations of the lines corresponding to the original equations. Okay? Any questions on that? Cool. Now, what do you think is going to happen here? This was our infinity of solutions. Are the lines going to intersect at a point? What do you think the lines are going to do? They're the same line. They're going to overlap, right? So the line for the first equation is the same. It goes through 1 and minus 1/2. Okay, so this is x minus 2y equals 1. But the second equation is pretty much the line for the second equation is the same as the line for the first equation, because if you divide each side by 3, you get the original equation. So the green is also going to be here. This is also 3x minus 6y equals 3. And the two lines overlap, and every place that they have a common point for is a solution. And so you can see there's an infinity of solutions. This overlap. So this is infinity of solutions. What do you think is going to happen in the last case? They're parallel. The first equation is the same as before. And the second equation, okay, so I'll take a volunteer for this one. Actually, why don't you finish the story? Can you give me draw the line for this one? Where the intersects? X-intersect is at 4, and the y-intersect, okay, as long as I know that, I can draw the line. This is 4. Figure not drawn to scale. So these two lines don't have any intersection. This is x minus 2y equals 1, and this is 3x minus 6y equals 12. When y is 0, x is 4, and you're going to get a parallel line. So geometrically, the three cases that are qualitatively different correspond to intersecting lines, overlapping lines, and parallel lines. In higher dimensions, if you go to 3 dimensions, then you're looking at planes, intersecting planes, parallel planes, overlapping planes. Okay? Are we all good? You need a break? Bonsai! Okay, take a 2-minute break. I take the silence as meaning that you need a break. Okay. I think we're ready to move into a matrix vector formulation of our problem. And so I'm going to introduce vectors and matrices and rewrite what we've done and talk about some of the basic operations on vectors and matrices. So we have a common language to go by going forward. So in the remaining part of the lecture, I'm going to talk about vectors and matrices. The way I'm going to write vectors on the blackboard is with an underline. In some of your notes, you'll see an arrow. In some texts, you'll see the letter X in bold. I obviously can't do bold on the blackboard, which is why I use the underscore. Use whichever one you're comfortable with. It doesn't matter to me which one you use, as long as you communicate clearly to us that what your notation is. Okay, so a vector X, which consists of, is essentially a column array of numbers where the number of entries in that column array is the dimensionality of X. So we say that the vector X belongs to Rn if it has n components, and each of those components is a real number. In later classes, you will find complex valued vectors, in which case so if X, in which case we denote that by Cn, where the vector X is complex valued. So if even a single entry in X is a complex number, that vector will be in Cn. We will deal almost exclusively with, if not exclusively, with real vectors in this class. Okay, now, so vectors live in this space called Rn. We say, so if X and Y live in Rn, we say X is equal to Y if they're equal entry-wise. We say if they're equal entry-wise. In other words, Xn equals Yn for every n from 1 to capital N. Okay? You look at the corresponding entries. If they're all equal, the two vectors are equal. We can define a vector z, which is the sum of, actually, let me do the scaling first. I'll do the scaling first. We can define a vector z, which is alpha times the vector x, where alpha is a real scalar. And z would then be entry-wise multiplication of x by the parameter alpha. So if I were to put z1 through zn, then z small n is alpha xn for every n. I mean, these are common sense definitions. There's nothing fancy that I'm saying, really. So to scale a vector by a constant, you scale every entry. So an example would be let's say 1, 2, 3, 1. This is x. So x is 3, 1. What space am I living in? R what? R2. Then what's minus x? What do you do with that? What are the coordinates? Quick, quick. -3, -1. And if I were to draw that, it would go down to -1, -3. It's essentially that. So that's z. Okay? If you multiply it by 2, you keep the same direction, double the length, and so on. Fairly straightforward. So this is scaling. This is equality, and this is vector addition. So I say that z is the sum of two vectors x and y if, when I look at each entry in z, it's equal to the corresponding sum of, or the sum of the corresponding entries in x and y. So entry-wise addition in x and y produces z. And let's look at this geometrically. Let's say, what's a good picture? So let's say I have two vectors, x is 4, 1, and y is 2, 3. So let's draw those. Four, 1. So that's x. And y is 2, 3. So that's y. Can you draw z for me? And then after you're done with that, so z is x plus y, draw that please, and then draw the vector q, which is x minus y. And see what you get. Draw it on the picture. Make sure you talk to each other and compare answers. Who was last? I forgot. You were last? Did you pick somebody? Red jacket, second row. You've been selected. You are? Philip. Go for it, Philip. So can you tell me what z is?
Z is
6, 4. Graphically, if I want to draw it, what would I do? Here's my yellow.
You can draw a vector perpendicular to, parallel to x
Uh-huh.
from the end of y.
End of y, okay. Parallel to x at the end of y. Uh-huh. And connect the origin to that. So it's the parallelogram. Did I go too far? I did go too far, huh? No, that's fine. So this is z, okay? So you have a parallelogram, and the sum of the two vectors is the main diagonal on the parallelogram. What about the other one?
The other one, q is equal to 2, -2.
2, -2. Entry-wise subtraction. So x minus y is the same as x plus -1 times y, right? So whichever way you like to deal with it, you can apply the scaling and then do the addition, or just subtract every entry in y from x, whatever suits your fancy. Okay, so where's that vector?
It's like connecting the end of y to the end of x.
So you're jumping a step. First, let's draw 2 minus 2. 2 minus 2 is here. Let's do orange. This is q. But as you know, we can translate any vector across the plane and get an equivalent vector. If you're dealing with physics, it's the direction that the force is pulling at it that's important, right? So this is q. So this geometric intuition, pretty much most of you I would have expected to know this one. Some of you may not have seen this picture before. So when you're adding two vectors, x plus y, you take the main diagonal of the parallelogram. When you're subtracting y from x, the vector you get is the line connecting the tips. The one that gets the arrow is the one that doesn't have the negative sign. So here, x is the one that doesn't have the negative sign. So x takes the arrow, and that's x minus y. Okay? So this is a geometric picture of vector addition. And in fact, by introducing the subtraction, I've introduced another operation among vectors, which is called linear combination. And this is going to play an important role in our storyline in the coming lectures. So if I have a bunch of vectors, a1 through an, let's say these are in Rn, let's make them Rm. So I have n vectors in Rm. A vector z can be obtained by a linear combination of these n. This is called a linear combination of these vectors. So whatever space these, so you can't linearly combine vectors that don't live in the same space. They all have to have the same number of components. That's expected, otherwise you can't even do the additions. So alpha 1 through alpha n are scalars. Okay, so you take a scalar, scale the first vector by some number alpha 1, scale the second vector by some number alpha 2, and do this all the way to an, your last vector, and you will get another vector that lives in that space, and this is called z is a linear combination of a1 through an. And very soon, when I talk about the notions of span of vectors, this idea will come back. So we've had vector equality, vector addition, vector subtraction, and linear combination. Let's see, what else do I want to say about vectors? There is another operation between vectors that we'll say a lot more about later. I'll just introduce it now and then leave it as is. And that is the inner product. Or some of you might know it as a dot product. Of vectors. I won't delve too much into this. I'll talk about it much more later. But for now, let's take two vectors x and y that live in the same space. The inner product of x and y is a function from r, let's see, from Rn by Rn to the scalars that is defined in this way. x1, y1 plus x2, y2 plus xn, yn. In other words, when you look at x, and you look at y, x inner product with y is obtained by pointwise multiplying x and y and summing. That's what this is. So you take the first component multiplied by the first component of the other guy and do this for every component and then add them all up. So this is xn, yn, n goes from 1 to n. This operation so it takes two vectors and it produces a scalar. This operation on vectors has to do with what some of you probably know as projection, and projection will play a very important role in some of the future topics. That's all I'm going to say about inner products right now. We'll get back to that a little later. Okay. Now, in the remaining time, I want to talk about matrices. So a matrix A is typically a rectangular array of numbers where if all the entries are real, then I'm going to use real here. If there's at least one entry that's complex, I'm going to use complex. Again, in this class, we're going to deal exclusively, almost exclusively, if not exclusively, with real matrices. This is called an M by N matrix. It has M rows and N columns. So the equations that we dealt with earlier with Gaussian elimination, those are all involve 2 by 2 matrices. If M is equal to N, in other words, if the number of rows and the number of columns is the same, then we say A is a square matrix. Equality works exactly the same way as in the case of vectors. So we say two matrices A and B are equal if A mn is equal to B mn for all m rows and all n columns. So a prerequisite for two matrices to be equal is that they have to be of the same size. If they're not of the same size, you can't even talk about equality. So two matrices are equal if they're, first of all, the same size, m by n, and their corresponding entries are equal. scaling works exactly the same way. So alpha times A means you're looking at a matrix where every entry is multiplied by alpha. And addition works the same way. So we say C is equal to A plus B if CMN is equal to AMN plus BMN. So the corresponding entries have to be added to create the matrix C. So nothing too exciting here. But more interesting things happen when we bring matrices and vectors together to model in shorthand some of the stuff that we've been talking about. So for example, let's look at our original example of two equations and two unknowns, x minus 2y equals 1, and 3x plus 2y equals 11. Yep. We can write this in matrix vector form in the following way. I take all my coefficients and compile a matrix that I call the matrix A with them. So this one has a coefficient of 1, so that top left entry is 1. This is minus 2, this is 3, and the bottom right is 2. This is my matrix A. My x and y are the unknowns, and I'm going to call this the vector x. And on the right-hand side, I have 1 and 11, and I'm going to call this the vector b. So this system of two equations and two unknowns is, when written in matrix vector form, ax equals b. And this is an equation that you're going to see many, many times in the coming weeks. The way we do the matrix vector multiplication is suggested right away from the way I wrote these equations, this matrix vector form from the equations. So if you look at the top equation, 1 on the right-hand side. So first of all, what are the dimensions here? What are the dimensions of A? 2 by 2. And x is 2 by 1. When you multiply a matrix by a vector, the right dimension here, the number of columns, must match the number of rows in the vector, or the number of entries in the vector. So these two numbers have to match. If they match, you're golden. And what is produced is of dimension 2 by 1. And that's exactly what this is, 2 by 1. So if I have, in general, an m by n matrix multiplying an n by 1 vector, or an n vector, what I get is a b that is m by 1. You've got to keep track of these dimensions. If somehow throughout your derivations the dimensions mismatch, then you've done something wrong. Now, so 1 on the right side is obtained by multiplying this 1 by x, this minus 2 by y, and adding them to produce that 1. Okay? So this entry times the first entry, the next entry on the first row times this entry gives you the first entry up here. And the same is true for the other one. So 3 times x plus 2 times y gives you 11. So that's how we formulate these matrix vector multiplications. In general, any questions on what I've done? Okay. In general, if I have an m by n matrix multiplying an n vector, what I have is A11 through A1n and AM1, AMN multiplying x1 through xn. And what would be the top left entry of, oh, whoops, I get a vector. What size vector do I get? This is m by n. This is n by 1. What do I get here? M by 1. What's the first entry? Actually, now I remember why I had it wide. So the first entry is A11 times x1 plus A12 times x2 all the way to A1n times xn. So the first row times this, component-wise. Second row times this will be the second entry in my vector, and so on. One thing that I forgot to mention about vectors is that when I don't say anything else other than the symbol and the underscore, I mean a column vector. There's this other notion, there's this other type of vector that will pop up very often, and that is a row vector. So you may want to go back to your notes on that section. So if I say, for example, RT, T stands for transpose, and that's a vector from, let's say, it has n components. This T is called transpose. And it's basically taking a column vector and flipping it 90 degrees counterclockwise to make it a row vector. I will always use a transpose if I'm talking about a row vector, just so that there's no confusion. Some textbooks make the reader decide based on the context whether a particular vector is a row vector or a column vector. I will always use this. Am I out of time? Let's see. No, I've got 2 minutes. Ha! Get the maximum mileage. Tell your parents, I'm getting maximum mileage from my class. Okay, so the same idea is true for matrices. So the transpose of a matrix, if I call this a hat, I have this hat trick that I use very often to keep things straight in my head. So if I define a new matrix A hat, I guess some of you there can't see this because of this wall. A hat, which is the transpose of A. All this means is that every entry in A hat is obtained from the mirror image along the diagonal, across the diagonal from the other matrix. So for example, A hat 3, 1 is obtained from the 1, 3 element of the original matrix. Basically, you take, if I have an A, B, C, D, if this is my matrix A, then A transpose will be what? What happens to the diagonal entries where these are equal? They stay the same. So A and D are the same. What happens to these two? They're swapped. Okay? I think that's where we should stop, and then I'll continue next week.